Hi everyone, welcome back. So this is another data analysis video and I am still recording a series of videos about probability distributions, and in this video I'm still covering the subject of the binomial distribution. So in the previous three videos to this I recorded some information about how to manually calculate the probability mass function and the cumulative density function for the binomial distribution, and we did that manually, and then we used the math library and SciPy to achieve kind of the same ends. So what I'm going to do in this video is kind of just this is, you'll probably be pleased to know, this is the final video about the binomial distribution. I'll move on to something different but related after this, another probability distribution. But what I'm going to do in this video is kind of simulate some data that follows a binomial distribution. So simulate a variable, a random variable that follows a binomial distribution, and then look at ways to investigate that data. So it's kind of repetition of stuff I've already covered a little bit, but also some new stuff around simulating variables. So just a quick recap about the binomial distribution. It's a discrete probability distribution and it's used to model the outcome of a given number of trials for some random process or experiment. And the outcomes can take one of two values, success or failure. And so these are not judgment values, and success is just any time an event of interest occurs, and failure is the occasions when it does not happen, it doesn't occur. So the binomial is defined using, there are actually four parameters, but I've summarized them in two here. The two kind of main things to keep in mind are the two parameters for the binomial are there's the probability of success on any given trial, and this probability remains the same for all subsequent trials, and the outcomes of those trials are independent of each other. Okay. And the second thing that is important to remember is the number of trials conducted. So this is fixed beforehand when we're looking at something using a binomial distribution. And the binomial can tell us how likely it is to observe k number of successes on n number of trials of whatever this process is that we're modelling, whatever the experiment is we're conducting. So a common toy example of a process that follows a binomial distribution is repeated tosses of a coin, so a fair coin probably, and we may be interested in the probability of achieving 12 heads in 20 flips of a coin, which is fair. If it's fair, it will have a probability of 0.5, 50% chance of coming up heads. So here, let's say observing a coin landing on heads, we could classify as a success, and observing a tail, we would be a failure outcome. And if the coin's fair, we'd have a probability for each flip of 0.5, 50%. And note also that each coin toss is independent of those prior to it, though. So each coin toss is not influenced by the coin toss that occurred before it. So prior events don't influence the outcome of the current coin toss or coin flip or trial, whatever you want to call it. So this independence of trials is a necessary condition for a random process to be considered a binomial process and to have the characteristics of a binomial distribution. And what I'm going to do in this video is kind of use the SciPy binomial method called Binom to generate and simulate a data set that follows a binomial distribution, and then we'll investigate the properties of that distribution using the PMF, the probability mass function, and the CDF, the cumulative density function. Okay, so to start with, in this code cell, I'm just going to import some libraries that will be useful. So I'm importing pandas as PD, numpy as NP, matplotlib, .pyplot as PLT, seaborn as SNS, and also, because we're going to use SciPy, I'm going to import the whole kind of stats module from SciPy. We're going to do I'm importing matplotlib and seaborn because we're going to create at least one plot. Okay, so having done that, let's generate some random data that follows a binomial distribution. And so what I'm going to do in this cell here, simulate data that models a series of coin tosses using a fair coin. So to do this, I need to make use of the SciPy binom method to specify the distribution. And I'm also going to make use of the RVS method, or random variates method, that generates random variates of the type specified. So in this case, it's going to be binomial. So what I'm doing here is I'm creating a new object called fair_coin, and I'm setting that equal to stats.binom.rvs. And then the arguments I'm passing, I'm asking for each trial n to consist of 10 coin flips. So one coin flip isn't a trial in this case. 10 coin flips is one trial. Yeah. And then I'm specifying we want a probability of success of 0.5 on each trial. And then the size here, the argument here is specifying we want 10,000 trials essentially. So 10,000 times 10 coin flips with a probability of success on each flip, each trial of 50% of 0.5 is what this is going to create for us. It's going to create an object that is an array or a vector of simulating a random variable for 10,000 trials. So quite a large variable, I guess. And then what I'm doing underneath is I'm using a print statement. I'm going to create a cross tab that shows the actual counts from the data we've simulated here. And it's the columns equals fair coin, so the columns are going to map onto the kind of arguments we specified for this particular object. And then I'm creating a data frame from our fair coin object and a histogram, so we can see. So we'll have a table that shows the frequency of how many trials 0 heads came up, how many trials 1 head came up, how many trials 2 heads came up. So we'll have a cross tab for that, but we'll also have a histogram of that same data. So let me run this and I'll say one or two other things. There we can see. So here's the cross tab. We see this top, the heading for each column is the possible outcomes: 0 heads, 1 head, 2 head, 3 head, all the way up to 10 heads, and it shows you how many trials that occurred. So 6 trials there were 0 heads, 7 trials there were 10 heads, 2,471 trials 5 heads came up, and you can see the distribution there. So this is a discrete distribution, the binomial, as the outcome can only take on certain values. 1 success, 2 successes, etc. So for each trial, this is the number of heads in 10 tosses per trial. Okay, so the possible outcomes are therefore 0 through to 10 heads on each trial. That's the reason I set the number of bins equal to 11 here on the histogram, so we can plot exactly each outcome and the frequency with which it occurred. Okay. So what we can see above in this cross tab is we can see the given number of heads that occurred in the 10,000 trials, from inspection of the histogram and the table, the frequency and therefore the probability of getting 0 heads here or 10 heads in a row were quite low. So we got only 6 trials came up. Did it occur that there were no heads at all came up, and only 10 trials did it occur. And only 7 trials did it occur that 10 heads in a row came up. Okay, so intermediate frequencies were much more common, and this distribution here kind of looks like it's normally shaped, but it is modeling a binomial process. Okay. So we get a fairly balanced and symmetric looking distribution with the fair coin example, because the probability of success and failure was set at 50%, so 50-50. If we used a different probability of success where the outcomes weren't equally likely, as is the case in many real-world scenarios that follow a binomial distribution, we'd not get this same shape of this same sort of symmetric-ish distribution. So let's investigate this further using different probabilities of success. So what I'm going to do now is, it's similar to the above example. I'm going to simulate data from 10,000 trials again, 10,000 trials of 10 flips, where but on this occasion, we're gonna pretend the coin's biased, and there's a 0.8 or an 80% chance of success on any given trial. So rather than it being 50-50, they all come up heads, it's now 80-20, they'll come up heads. So you can see here, I've created a new object called bias coin. We're kind of simulating a completely new, we're creating a new object, simulating a new variable, and the only thing that's really changed is this p-value is now 0.8. I'm going to do this exactly the same thing here and specify, create a data frame and also a histogram. So let's have a look and see what we get. And what we should see in this case is we get a much, with the bias coin, where success is more likely, it's an 80% chance or 0.8 probability. We're seeing a much higher frequency of larger numbers of heads come up on each trial of 10 tosses. So in this particular simulation of 10,000 trials, we can see that there were no occasions when 0 came up, and very few. I've put no occasions when less than 3 heads were tossed in a 10 flip sequence. That's not true. There were on one no. There didn't seem to be no occasions where 0 came up. No occasions where 1 came up. 1 occasion where 2 came up. 6 occasions where 3 came up. Okay, so this distribution is now much more skewed. In this case, in the negative direction, the tail is towards these lower numbers. Okay, so changing the probability of success changes the shape of the distribution. Okay, so we can use the cumulative density function, the CDF, to work out probabilities of certain outcomes or less for this simulated data that we've got here. So SciPy provides the CDF method to allow us to easily compute this. So we did this in a previous video, using the cumulative density function is useful. It'll tell us what's the probability that we'll get 5 or less heads, 5 or fewer. So we can obtain specific probabilities that a number of successes from 10 trials in our data set is less than or equal to a certain, let me just correct that, apologies, certain value. So for example, if we're interested in knowing the probability of getting k equals 5 successes or less with 10 flips per trial at a success probability of 0.8, then the arguments for the CDF method here are k, which is the number of successes we're interested in, n, the number of trials, and p, the probability of success. Okay, so to run that, it's just stats.binom.cdf, and we're passing k, n, and p. And what we see is we get a probability of 0.03279, etc. So if we round that to 2 decimal places, what we're seeing is we've got about a 0.03 chance, a 3% chance of getting 5 heads or fewer with our bias coin. So that kind of fits. I guess that fits with what we're seeing here. 5 or fewer. There's very, very rare occasions when that happens. Much of the density is kind of above that. Okay, we can also check the probability of getting more than a certain value using the CDF by taking the complement. So we're going to subtract the CDF from a total probability of 1. So in the previous video, I kind of demonstrated a similar thing using in SciPy using the survival function, the kind of .sf method. But we can kind of do this calculation another way as well. So to work out the probability of getting 8 successes from 10 flips using our bias coin with a success probability, we simply do 1 minus the CDF. So in this example, This will tell us the probability of getting 9 or more heads in a trial of 10 flips. Note that we're setting k, the successes, to 8 to get anything higher than that value. So if we just did our normal CDF on this, this would tell us the probability, it gives us the probability of getting 8 or fewer. Because we're interested in specifically more than 8, so 9 or 10, we do 1 minus the CDF, essentially. So what we're saying here is 1 subtracts the probability of getting 8 or fewer, which will give us a specific probability that we would get 9 or more, essentially. Let's run that. What we see is it's about, if we round it to 2 decimal places, it's about 38% chance, 0.375 probability of getting 9 or more heads in 10 flips with our bias coins. So still quite high. Okay, so the CDF gives us the cumulative probability for all values up to a certain number of successes in the distribution. Or conversely, if we take 1 minus the CDF, the other side of the distribution using the complement. So to check the probability density at a given k value for number of successes, so a specific number of successes, not that number and lower or anything above that number, just a given value for successes, just the probability of getting that value and not a value plus or lower or higher values. We reduce the probability mass function, the PMF, as the binomial is a discrete probability distribution. So SciPy has a PMF method that makes these calculations easy for us to run. So let's have a look at that. Okay. So as an example, we can use the PMF to work out the probability of getting exactly 5 successes from 10 flips with our fair coin. So our fair coin being a probability of set 0.5, yeah. That's what that should be. Sorry, I'm correcting my errors as I go along. So here's what we're going to do. We're going to use the stats.binom.pmf method, and the arguments we're going to put are k, which in this case is the exact number of successes because we're using a probability mass function, the number of trials, which is n, 10 trials, and the p-value is our success probability on each trial, which in this case is 50% or 0.5. So if we do that, what we see is we get about a 25% chance of getting exactly 5 heads from 10 trials with a success probability of 0.5, a 50-50 chance. Okay, so as an alternative example, we could also do a similar sort of thing, the probability of getting 8 successes from 10 flips with our bias coin. So that has a success probability of 0.8 for each chance. So here we're specifying k is our exact successes, as 8, n is the number of trials, that's 10, and p is our probability of success on each trial. And this time we've kind of loaded it to about 80%. So again, using the stats.binom.pmf argument, and what we can see is in this example we've got about a 30%, so if we round that to 2 decimal places, 0.30, we've got about a 30% chance of getting 5 heads with our bias coin. Okay, so quick summary of what we've covered here. So the binomial distribution is a discrete probability distribution that models the number of successes for a fixed number of trials, where each trial has a set probability of success, of a successful outcome being observed. We can simulate data sets of different sizes that follow the binomial distribution using SciPy's binom method and the random variables method. So that's what we did. We simulated quite a large variable, so kind of about 10,000 observations of each trial. We could create further variables and put them all together to, in order to use a variable that followed a kind of binomial distribution in some sort of analysis. But we can, if we've got a variable that follows a binomial distribution, we can investigate the properties of that distribution using the CDF and the PMF, the cumulative density function and the probability mass function. The CDF allows us to calculate the cumulative probability of getting a certain number of successes or less, and we can also calculate the complement, that's 1 minus the CDF, to find the probability of getting a certain number of successes or higher. The PMF, the probability mass function, allows us to calculate the probability of a specific success value. So exactly what's the probability of getting exactly 5 heads from 10 trials with a coin that's with a coin that's 50-50, got a probability of success on each trial of 0.5. Okay, this tells us the proportion of observations at a given number of successes. Right, so that is the last I'm going to do for now on the binomial distribution. That's like 4 videos I think I've done. Hopefully this was interesting and useful, and over the last 4 videos about the binomial we've kind of developed some intuition about it and how it works. As you can see from changing the probabilities, the shape of the distribution changes when we do that. In the next video what I'm going to do is move on and talk about the Poisson distribution, which is similar to, it's related to the binomial, but it's used for, it can take continuous values as well, so it's often, rather than specific events, it's kind of often used to model rates at which events occur. All right, thanks for watching and listening, and I shall see you soon.